So guys, today we have, in our mini lecture, we are going to address formal charges. So in yesterday's class, we were talking about resonance structures and how different compounds, covalent compounds, could take different shapes, and that sometimes they actually suit and fit the octet rule, but one is going to be more predominant than the other, prominent. So what I would like to do is just simply go back in and talk to you just very quickly and say, remember how to get the valence electrons. All the elements in the first column have 1. The elements in the second column have 2. 3 valence electrons, 4 valence electrons, 5, 6, 7, and then of course 8 would be our magic number. So with that being said, I'm going to look at the 2 different resonance structures of CO2, and then we're going to see which one is going to be more prominent. So let's go through and just draw the CO2. So first of all, I need to know the valence electron count. So I have carbon, which has 4, and then I have 2 oxygens, which is going to have 12, so that gives me a total of 16 valence electrons. So when I do this, I'm going to end up with 4 being used. That leaves me with 12. So that's 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And guys, there's a mark on that paper. We're just going to have to work around that. So I look at this. I've used all 12 of my electrons. This oxygen is at the octet. This oxygen's at the octet, but my carbon is only at 4. Has 2 shared here and a pair shared here, so that's 2, 4 electrons. So we can draw this one way and just simply say, okay, let's take those and let them share and make a double bond. Now, let's take these that are on that oxygen and let them be shared. So at this time, I have 2, 4, 6, 8 around the oxygen, 2, 4, 6, 8 around this oxygen, 2, 4, 6, 8 around the carbon. So that is going to be one of the ways that I could write this. Now, the other way that I could write this, and I'm going to do the exact same thing, carbon, oxygen, and oxygen. I've already done this, so I'm not going to spend a whole lot of time explaining that. So back to the same point. I've used all of my valence electrons, so I don't have any more electrons. But this time, instead of just making a double bond right there, what if I was to make a triple bond? So if I make that triple bond right there, what that's going to end up doing is now I have 2, 4, 6, 8. I have 2, 4, 6, 8. So my oxygens are good. My carbon has 2, 4, 6, 8. So both of these structures can happen. But what we're going to find out in chemistry, one has to be more prominent than the other. So that is where formal charges come in. How do you determine the formal charge? Well, it says you take the number of valence electrons and you subtract what the element starts with. So, I'm sorry, let me try that again. Okay, the number of valence electrons, and then you subtract the number of valence electrons assigned to that atom. So let's go through and look at this. Number of valence electron for oxygen is going to be 6. For this carbon is 4. For this oxygen is 6. Now, if we have the dotted electrons being assigned, that means that those electrons are only assigned to that oxygen. If you have a bond, then that means that the electrons are being shared. So you only actually have 1 assigned. So if I go through and I count this, I'm going to get 1, 2, 3, 4, and then 5, 6. So I'm going to say minus 6. And what that does is that tells me that I have 6 electrons assigned to that oxygen. 1, 2, 3, 4, and then each one of these are only going to represent one of them because the other one is being shared, so that's 1 and 2. So with my carbon, I have a valence of 4. Now I'm going to say 1, 2, 3, 4. I have 4 assigned. And with this one, it's the same thing. Minus, I have 6 assigned, so I get 0, 0, 0. Now, I'm going to take it, before I explain, I'm going to come back over here and look at this one. So on this one, I still have 6, 4, and 6. So this time I have 1, 2, 3, 4, 5, 6, 7 assigned. On this one I have 1, 2, 3, 4, so I still have 4 assigned. And then on this one I have 1, 2, 3, 4, 5 assigned. So I just get a 1 for that one. So basically, if it is a compound, okay, that's what it's saying. The total formal charge of a neutral molecular compound should be 0, and you should get zeros on the total number of charges for each one of the elements. So you see how I've got -1 here and a 0? Okay, even though that follows the rules, it would not be an accepted, or it would not be the most prominent. This one would, because it is much more stable. Now, I'd make another statement right here, and I want to go back over it, and it says, if you have a polyatomic ion, the sum of the formal charges should be equal to the overall charge of the ion. So if I was to do this and I had, and I'm just going to choose CO3 minus 2. All right, I'm not going to work this one all the way out. We're going to do this as a practice problem in a few minutes. But do you see how this is not a molecular stable compound? This is an ion. This is a carbonate ion. Carries a -2 charge. So when I did the formal charges on this one after I drew it up, then I would expect to have an overall charge of -2, because that is the actual charge of my carbonate ion. All right, so what were you supposed to get out of this? Well, this is a continuation of what we were doing with our resonance structures. Sometimes the resonance structures, it just changes where the bond's located, but sometimes they can take a complete, total different one. CO2 is probably one of the most predominant. Another one that you might want to be familiar with is silicon dioxide. And the reason being is because silicon dioxide, silicon is in the same family as carbon, so it's going to be set up the same way. So on a test, AP test, if you're asked to do formal charges to determine which is the most prominent, you will either get this or this. All right. I hope that has helped you, and we'll continue with the next mini.